Good morning. I plan to speak English. I think I will proceed like this. Thank you for invitation to this conference. I promised to visit it, visit Uzhhorod, but I want to do it, but unfortunately I catch the cold, so sorry for this. It's semiconductors. My area is superconductors, and I almost know nothing about semiconductors, and I always felt that there is very different camps, different communities, and people speaks different language also. And one of the aims of this presentation is just to try to fill this gap. Of course, there are, especially now, I see that it is really time to do so. Therefore, I wanted the structure of my talk. I wanted to give some extended introduction, which should be entertaining and educational, and therefore highly speculative. And also I would like to connect it somehow to our recent results on superconductors, of course, but nevertheless, I think that our plans should to involve semiconductors. So I understand that I need to fit in this popular introduction and about electronic structure, and I think it is the electronic structure. All these terms, I think they are differently used in community, in metal and in semiconductor communities. Therefore, I need to define these terms, I think. And when I speak about electronic band structure, I'm speaking about this electronic bands, and this is important to speak about scales, energy scales of interest. And when I speak about electronic structure, this is already a bit more because electronic band structure it is just like a frame or skeleton for the electronic structure, because electronic structure includes also interactions, and if we have bands and plus two bands, we have effects of interaction. And electronic structure already described in terms of spectral function, one particle spectral function, and this is what we see in experiment. This important materials for us, it is superconductors, which I need to introduce somehow. I mean that a lot of things I should introduce, but superconductors, superconductivity, and Josephson junctions, and superconducting qubits, I would mention again in terms of scales, energy scales. And the same about topological insulators, topological states, from topological state from topological insulator to topological superconductivity. Also, finally, I wanted to mention like a quick review, very quick review. This is examples of potential interest directions, how now this superconductor semiconductor interfaces are developing now in the direction of construction of superconducting qubits. Finally, this is about our recent result that give us possibility to utilize our knowledge about electronic structure, about Fermi surface, for construction of quantum devices. And I think especially here, the role of semiconductors would be crucial. So what I call electronic band structure, this is just a slide from my lectures to students. I mean that we have, let's say, in approximation of small potential, big potential approximation, we have a brilliant zone, since we have a number of replica of free electron parabola. And we have band gaps, which we call band gaps at the boundary of the Brillouin zone, or at every place where the replicas cross the main band and each other. And this form the bands, and what we call bands, we call this in one dimension it will be line, in 2 dimensions it will be surface, in 3 dimensions it will be already more complicated thing. But I just in metal physics, in superconductors, we call conducting band. It is half filled or partially filled band. We call conducting band, right? And all bands which are below the Fermi level, we call valence band, and above the Fermi level, which are unoccupied completely, just unoccupied bands, right? And about energy scale, normal energy scale, it is about 5 electron volts. So from 1 to, of course, there are very different compounds and situations. But I would say that usually it is to have 5 electron volts as a bandwidth, and from 1 and above and even below, but I put here 1, it is the character value for the band gap. But also for us it is important much smaller scale, which is close to Fermi level, and the scale of this the value of the scale, the size of the scale, it is milli electron volts from 1 to 200, let's say, milli electron volts. That is defined by temperature, by interaction energy. And I will show you now example on superconductivity. But first, I would like to say more just educational stuff about Fermi surfaces, which are important for us, very important for us. That for 1D case, we have, for example, free electron parabola of part of the band, occupied band, like this, right? And Fermi surface, it is just 2 points here. And in 2D case, we have already paraboloid, and Fermi surface is just a ring. And in 3D, for 3-dimensional crystal, Fermi surfaces are like spheres. But of course, these are simplest situation, and even for simple crystallic structure of simple metals, you see that such a Fermi surfaces are only for very for only a few metals, but usually Fermi surface is more complicated thing. And this is especially for other materials. But a good thing about it is that the most interesting materials for physics, they are quasi 2-dimensional, and therefore we have this possibility to consider band structure as a surfaces, and actually electronic band structure, and spectra or spectral function, or this electronic structure, as I call it, we consider as this field of 3-dimensional space where you have two momenta and energy. And speaking more about superconductivity now and about scales in superconductors, we have the superconducting gap, which opens at the Fermi level, at the Fermi surface, and this is the order of let's say from 0.2 electron volts, or from 0.02 to 20. It is mistake here. 20 milli electron volts are down to very low values, and you see here just examples of known materials. But for understanding of superconducting qubits, one should also know about Josephson effect, Josephson junction. And Josephson junction, it is just a junction between two superconductors. There are a very large variety of different types of junctions, but idea is under Josephson effects that it is deal with tunneling of the superconducting pairs. Instead of just normal tunneling of electrons, we have tunneling of superconducting pairs. And for technical reasons, for using in as qubits, it is important that when you add to the circuit, if you add Josephson junction, it is highly nonlinear element, and this nonlinear element help you and you can adjust easily its parameters, and you have it's this rather macroscopic object. You can realize two or how many you need states, and you can operate them. And there are different types of superconducting qubits. They are charge qubits, flux qubits, and phase qubits, but also there are different modifications of it. But still, the most important parameter here, this energy scale parameter, is its superconducting gap. Its energy scale is defined by superconducting gap. And but it is really superconducting qubits are considered as very perspective, because you can see that most of the known companies, computer companies like Google or IBM and so on, they built their versions of superconducting quantum computers, and they have a lot of success, but also in parallel to this success, we should admit that it seems there is a serious obstacle, which is called the coherence problem, because these qubits, in order that quantum computer operates, you need to entangle a number of qubits starting from 1,000 and more. And now the record, at least a year ago, the record was this 127. This is IBM computer based on charge qubit, which is Transmon qubit. It is just like transport. The coherence looks a serious problem. On the other side, it is a good thing, because this problem could be considered that it is very sensitive system, and they could be used for sensors, but for quantum computing, it is a problem. And therefore, one should look for other alternatives about building of qubits, and alternating materials or alternating geometries of these Josephson junctions and properties. And for this, one of the most important or most promising materials considered topological materials, and in particular topological insulators, for example. This is just also a case to show you an example of experimental data, and brief introduction to ARPES, angular resolved photoemission spectroscopy, which allows you to see this actually electronic structure. So this is exactly what I call the electronic structure, and this is distribution. You can consider it as distribution of the fermionic spectral function in occupied part of the band structure, right? And it is easy because it is easy to measure, because experiment is simple photo effect. If you shine the material with photons of fixed energy, and you analyze the electrons, photoelectrons, then you analyze its energy and distribution angle. Therefore, you have you due to momentum conservation and energy conservation laws, you have you know its position in momentum space of the momentum energy space, the position of these photoelectrons which it had in solid. Therefore, you just can visualize very simply this electronic structure. And this is example of topological insulator. See, this is number of bands. It shows just a valence band, but at the Fermi surface, at the Fermi level, you see that these bands, it is topological state surface. It is topological surface states, which are metal, and if the Fermi level goes here, the material in bulk, it will be insulator or semiconductor, and because you see that the gap, this is between bulk states, it is between this and this approximately. You see it is 0.1 electron volt, so it should be semiconductor. And it is interesting about these materials that this topological surface states, they are, let's say, topologically protected. I will not explain what does it mean, but this also they have states. It is a number of states which has only one spin direction. This direction of spin is changing over the Fermi surface, but this is only one direction of spin, because another direction of spin is on the other surface of the sample. Why it is important for us? First, of course, it is stable materials. It is interesting that I mean its structure is really protected from different influences, let's say, and but also it is important thing that it is the place where people expect the realization of so-called Majorana fermions. So to quickly, I just want to briefly pin the three directions. So in this interfaces, superconductor, semiconductor interfaces for superconducting qubits. So first one, it is just simple, I would say, simple realization of Josephson junctions with the help of some low dimensional semiconductors, because for Josephson junctions, it is the parameters, it is important to have very required, very fixed value of conductivity and capacity, and combination of it for combination such kind of geometry where you have superconductors and they are connected by bad conductivity, let's say tube or one-dimensional object, it would be very nice. It would be much better than planar geometry, which is used in superconducting qubits now. But it is technologically much more difficult to make reproducible. Therefore, it is just a technological question, but it is interesting direction how to evolve. Another thing, another good thing about semiconductors is that they are easy to change their properties by gating, and therefore you can vary the properties of this. Let's say this is example how people vary the properties of qubit with such a gating idea, and it is called gate modes. And finally, I want to say a couple of words about this Majorana fermions, or now it is preferred to call them Majorana zero modes. And for this, I could refer to the science paper, but mainly because they put a Majorana picture of Arturo Majorana here on the cover of Science of this science issue. But to get introduced in this topic, I would recommend this lecture on YouTube. Patrick Lee, he explains in simple words where it comes from, and the idea. It starts from idea about excitation, that to describe one particle excitation, you have something like this. You have electron excitation, but when you cross and below the Fermi level and excitation below Fermi level, they actually, of course, has energy also more than main state, and therefore the dispersion should be like this. In experiment, in ARPES experiment, of course, we have only occupied states, but it is also important that if we have superconductors, and in superconductors we have this gap opening, this opening of the gap also gives you just a mixture of Hall and electron states, and therefore it was shown that this mixture, if you define another particles like through these fermionic operators, and this means that you have defined two other operators, and these two other operators will be real, not complex. And this means that particles which are described by these other operators, they are equivalent to their antiparticle, and this is a definition of Majorana fermions. But what is important, if you have such a kind of dispersion, such a kind of mixture of electron and Hall states, that these states became localized in space. And this means that each, let's say, fermion could be presented by two locations by two, which are called Majorana zero modes, and they are connected. They are coherent, they are entangled, and therefore they could be used in manipulation, and they are very stable. They are much more stable than this states of qubits, superconducting qubits, which I described before. And now I switch to this, let's say, state-of-the-art technology, which is called aluminum technology. It is plain contacts. So aluminum is not best material because TC is very low, and it means superconducting gap is very low, but it is very technological, and aluminum oxide is very technological since and very reproducible, and therefore this is state-of-the-art technology now. But as I said, it is the energy, it is the main problem, it is the coherence. And the coherence, even at extremely low temperature, ultra low temperature, we have the coherence problem because the energy at which these qubits speak to each other, it is proportional to the superconducting gap. And if you want to increase this, you should try to include to make this Josephson junction with superconductors with higher gaps. It is more technologically difficult, and it is also difficult because for this superconductor you usually have sign change of superconducting parameters. It is of course a special topic, very big, but I want to say that we were the first who managed to realize the Josephson junction with between normal, let's say, niobium superconductor and the new iron-based superconductors, which are known that they have so-called S plus minus superconducting order parameter. That complex superconducting order parameter is changing sign, has different sign on different Fermi surfaces. And but what is the most interesting was about it that when we tried, it means Alexei Kaleniuk from our department, he did it in Stockholm, and he spends a lot of time to use this technology, to invent this technology to do it. And he found interesting effect that if he put a thin layer of copper in between niobium and iron-based superconductor single crystal, expectation was that the parameters, the junction will be better, but the parameters will be lower. But the parameters, which is ICRN, which is proportional to superconducting gap for normal superconductor, it increased 40 times. And this increase is related with the Fermi surface, as we understand now. That here we have, let's say, above we have niobium, and then in between and niobium, you see Fermi surface of niobium, it is very complicated. Therefore, the projection of the Fermi surface will be almost constant. But the projection of the Fermi surface of copper, it is very simple. It will be like a ring. And therefore, but Fermi surface of single crystalline iron-based superconductors, it is very defined, right? And but it is important that the sign, one sign of the order parameter here is, let's say, plus, and here is minus. And when we have just junction, when pairs jump from niobium directly to iron-based superconductor, we have destructive interference. We have jump into plus region to minus, and we have destructive interference. But when we put in between such a filter as a Fermi surface filter, Fermi surface works as filter, we can just cut only some channels, and it is really interesting. Because I think the next step should be to use here some semiconductors where we can Fermi surface, we can, by gating, we can change essentially. And it is interesting to try to do in this way. Okay, so that's it. I think conclusion will be simple, that I think it's really time for superconductors to meet semiconductors for quantum devices. And we are going to do it. And I welcome your interest in this direction and possible collaboration. Thank you for attention.
Let's thanks to the very interesting talk. And do we have any question?
You have shown a lot of qubits, but my question is about what kind of qubit is used now in the most modern quantum computers?
Yeah, I shown a lot of qubits, and I can't answer this question completely. But for example, the things which I mentioned, where they are, one moment, it is here, right? For IBM, it is written that they use Transmon superconducting qubits. And Transmon qubits, this means that this is just the simplest charge qubits, by just improved for some noise problems. And but other could use other geometries, but really now I think most of them really used this geometry of qubit, and also this aluminum technology, because it is technologically most simple. It is also not very easy, but it is most simple technologically. That's it. Yeah.
Okay, let's thanks again for the very interesting talk.